Nobody witnessed the formation of the solar system. So if astronomers are going to figure out how the solar system formed, they need to look at current day evidence. So what are some observations that people can make about the solar system that would give us clues as to how it formed? So the next few slides here are going to show some of those. First one here, and this one is interesting. This is sort of the grand scale one, I'd say, that all of the large objects in the solar system rotate on their axis the same way as viewed from above the Earth's North Pole, except for two exceptions. Sorry, bit of a redundancy there. But in the inner solar system, Mercury, Earth, Mars, Jupiter, Saturn, and Neptune all rotate counterclockwise as viewed from above the Earth's North Pole. Two exceptions are Venus, which actually rotates clockwise, and it rotates very slowly, and Uranus, which essentially rolls around the sun like a barrel. So for about half of its year, its north pole is pointed in the general direction of the sun, and for half of the year, its south pole is pointed in the general direction of the sun. So 6 of the 9 planets rotate in the same way. So that's giving us some evidence that whatever description we have, whatever explanation we have, needs to fit that. And if there's some other part of the formation that could address those 2 exceptions, then that would be great as well. Another clue is that the planets fall into 2 main areas. Terrestrial planets, so the inner planets are generally small and rocky, high density. The outer planets are large in radius, large in mass. They are primarily hydrogen and helium with a lot of ice, and especially their moons. They have a lot of icy moons as well. Oh, and by the way, all of the outer planets have rings. We think of Saturn as the ringed planet, but Jupiter, Uranus, and Neptune also have rings. Their rings were discovered much more recently. The rings of Saturn were discovered about 400 years ago or so. Again, we think of the solar system, we think of the planets, but there's a lot more out there. So there are asteroids and comets that surround the solar system. In the news recently has been the Kuiper Belt. Pluto is the most well-known member of the Kuiper Belt. That is fairly close to the rest of the planets. The Oort cloud is farther away. The planets orbit in a plane. Pluto is very close to being in that same plane as well. But these other objects form a sphere around that plane. And then I mentioned some of the exceptions. One of them here, this is showing Uranus's odd tilt, although I don't know if I'd call it odd. It's different from the others. And then most of the planets that have moons, their moons are a lot smaller than their host planet. Our moon is about 1/4 of the radius of Earth. Pluto, which is no longer classified as a planet, it also has a large moon. In fact, its moon, Charon, is larger compared to Pluto than our moon is compared to the Earth. Something else in the solar system, there is what the book here labels the frost line. So inside the frost line, the temperature at formation, so inside here, notice the thermometer here is high, the liquid in here is high. That indicates it's warm. So the formation of the solar system was too warm for ice or liquid water to form at that temperature. So inside the frost line, there could not be solid or liquid water. Outside the frost line, there could not be liquid water. So outside the frost line here, there is a lot of ice. So even in our asteroid belt, the frost line is right about where our main asteroid belt is. Some asteroids are predominantly icy, some asteroids are predominantly rocky. Jupiter's moons, Saturn's moons, Neptune's and Uranus's moons have significant amounts of ice. We think of water as being rare in the solar system. Liquid water is rare, although not as rare as once thought. Solid water or ice is not rare at all. This is just a diagram of how planets could form. So remember the one diagram I showed you, there were lots of particles or lots of small objects in the Oort cloud and the Kuiper belt around the main plane of the solar system. So this is showing one model here of formation, and this right now is assuming roughly what we're looking at is the top of a plane. And we'll talk about how it could have got into a plane in just a little bit. And remember, a plane is just something that is two-dimensional. Strictly speaking, I don't know if you'd want to call it a plane, because a plane has infinite length and width. This does not have, our solar system is not infinite, but still, things that are flat like that, even a piece of paper, we will typically say that that is a plane, even though it's not infinite in size. So here we've got a bunch of particles going around, and all particles, no matter what size they are gravitationally attracted to other particles. So you see here, some of them are a little bit larger, most of them are smaller. Those larger particles are going to have a slightly greater gravitational pull, so larger particles are going to draw nearby smaller particles to them, which means those larger particles are going to get smaller. Those larger particles are going to get larger, and there will be fewer smaller particles. So what started off as maybe some large medium-sized particles and some smaller medium-sized particles, you get to have some big medium-sized particles here and more empty space. And then those larger particles attract other larger particles, and we end up with a few very large particles, aka planets. And this doesn't really represent our solar system. It shows here the Earth as being what you'd represent Venus as, and this reddish color here, sometimes you represent Mars as that. So this is just some typical solar system. And by the way, if this truly was the scale, this would be a really tiny star compared to these planets, or these would be really gigantic planets compared to this star. What happened in the grand scale solar system, and I'll finish up with a large overview in just a bit, also happened with respect to the gas giants, also called the Jovian planets, named after Jupiter. So our sun is the massive center of the solar system, and there are a bunch of smaller particles, and I keep saying particles, that makes it sound really tiny. That's a generic term. They're called planetesimals. So planetesimals are smaller chunks that eventually form planets. That happened on the large scale around the sun, but that also happened on a smaller scale around the giant planets. So here's Jupiter. Jupiter's system is almost like a small solar system. Some people call Jupiter a failed star. That doesn't sound very good for Jupiter. It's not a failed star, but it's pretty close. If Jupiter was, I shouldn't commit to a number here, but maybe on the order of 10 times more massive, which isn't that big of a difference because it's a tiny fraction of the sun's mass, it would be a star. So it's a lot closer to being a star than Earth is, for example. But just like we had these rotating planetesimals around the sun forming planets, we have, and the solar system, by the way, is mostly hydrogen and helium, and the sun is mostly hydrogen and helium. Jupiter and Saturn are also mostly hydrogen and helium. So Jupiter is an object of mostly hydrogen and helium surrounded by icy chunks. The sun is a ball of mostly hydrogen and helium surrounded close by of rocky chunks, and farther out the gas giants. So this is a fairly complicated drawing, but this shows, this is a great summary of the solar system formation. So up here you see the solar system is represented by this cloud, this large cloud of gas and dust. And just like any old cloud of things, it's not going to be perfectly static. Typically in the outer space, there are things happening, what most people think of as the precipitate precipitate, that's not quite the right word. The starter of our solar system forming was a supernova. So the shock wave of a supernova was what got the cloud of gas and dust to initially start forming. So that cloud's going to be jumbling around like this. And as particles are moving, you're going to have particles that are moving in opposite directions sometimes. They collide with each other and slow down. That's going to happen on the grand scale. But what's initially a cloud of things all moving around eventually will evolve into something that's rotating all in the same direction. As this cloud is rotating around, it's going to flatten because, as I said, all particles are attracted to each other. Smaller particles accelerate more towards massive particles than vice versa. So if you've got a cloud of gas, most of the mass is going to be at the center, because if we cut across the center, you're cutting across the entire diameter, the top and the bottom. There's not as much mass around. So this cloud is going to start to flatten as it rotates. And then some of the larger particles here are going to attract some of the smaller particles, and you're going to end up with these planetesimals. The inner part of the solar system, the planetesimals are predominantly rocky and metallic because the temperature is too high for there to be water. There's still hydrogen and helium. Most of it is concentrated around the sun because the sun takes up most of the mass of the solar system. And in the outer part of the solar system, these planetesimals, there's going to be hydrogen and helium, but the actual solid particles, it's too cold. The metals and the rocks have already condensed in the inner part, so we've got the water ices and methane ices and so on condensing in the outer part. Smaller particles collide together to make bigger particles, and we end up then with what we call the planets. Fairly early in the sun's formation, the solar system's formation, I should say, but after the planets form, the sun becomes very active for, as part of its life, a fairly short amount of time. It has a very strong solar wind. The sun still has a solar wind, but not nearly as strong as closer to its formation. And that blows out the excess hydrogen and helium, leaving what we have now as the sun, some planets and moons. And this just shows on the plane here, comets, probably the Kuiper belt here. But there are objects in the Oort cloud that are all around the solar system. So, very brief summary. Cloud of gas and dust is rotating, collapses into a plane. That plane isn't uniformly distributed. There are going to be some more massive planetesimals, some smaller ones. The larger ones are going to attract the smaller ones. In the inner part, those planetesimals are primarily rock and metal because of the high temperature. They're called volatiles, things that heat off at a fairly low temperature. So here we have more of those things that would have evaporated in the inner solar system because the outer solar system isn't as hot. And the particles collide and form larger objects, and then we end up with what we have now as the solar system.